Oh, hello. My name is Silvio Dantas, and I'm going to talk a little bit about my research as a PhD student. In this video, we're going to discuss adsorption of water, its importance, and some more exciting stuff. Shall we begin? Let's begin with understanding the difference between adsorption and absorption. To illustrate the difference, let's say you get home really thirsty and you go to the kitchen to grab some water. But the cup slips from your hand and then you need to clean all that mess. Then you realize that you could use paper towel or notebook paper to dry the table. Most people know by experience that the paper towel is better. So let's discuss a bit the difference between them. In the case of the paper towel, absorption is the main process and occurs when liquid molecules are incorporated into the volume of the solid, becoming a single phase. On the case of the notebook paper, the adsorption is predominant and takes place when fluid molecules stick to the surface of the paper, where they can easily be removed from. In this case, the water is called adsorbate, while the paper is called adsorbent. Some certain materials are widely used for their adsorption properties, like activated carbon. These materials are able to adsorb large amounts of other molecules due to their enormous porous surface area. Only 1 gram of this material has 1,300 square meters of area. That means that only 4 grams of this substance would have the same area as an American football field. Then you think, oh wow, that is so big. But where is all the area that I cannot see? There are tiny pores within these materials. They can be as small as a few angstroms and as big as hundreds of angstroms. Molecules somehow enter these pores and can travel through, where eventually they get stuck to the surface. So to answer the question, the area is so big because there are so many pores, therefore a lot of surface to molecules to get stuck to or adsorbed. To illustrate better, let's talk about one very well-known application of activated carbon and adsorption processes, which is on the treatment of indigestion and also poisoning by oral ingestion. If you ingest a certain substance in large quantities, activated carbon might be the solution for reducing the amount of that substance in your body. Let's take aspirin's most important component, acetylsalicylic acid, as an example. It can cause stomach pain, but activated carbon can help by adsorbing the molecules, preventing them from being adsorbed into your body. So, activated carbon can be bought as an over-the-counter drug and can get you out of a very uncomfortable situation. Now we can talk about how I study these processes. A big part of my research is to use computational tools in order to mimic real-life adsorption experiments in a computer. Remember those little tunnels I was talking about earlier? We start with a box that represents them. Let us call it the system box. Another box, infinite in size, is used as a reservoir, where it keeps several adsorbate molecules. These two boxes are at the same temperature. Next, we perform moves on the fluid particles while keeping the solid particles fixed. The moves consist mainly of moving particles from the reservoir to the system box and back, translation moves and rotation moves. Moves can be accepted or not depending on the change in total energy of the system. The total energy of the system is calculated by summing up the energies between individual particles in the system. If they are too close, the energy is positive, which means that they repel each other. If they are too far away, the energy is negative and they attract each other. The lower the total energy, the more stable that particular configuration of the system is. So, in this kind of simulations, called Grand Canonical Monte Carlo simulations, we start with a system at a fixed temperature and chemical potential. Then we perform the moves described until changes in the system are negligible. As a result, we get the energy of the system and how many molecules are in it when in equilibrium. Now we can talk about the exciting part. From the experiments and simulations we talked previously, we aim to get several important results. One of the most important is the adsorption isotherm. As we discussed, from a single simulation at constant temperature and chemical potential, where chemical potential can be related to pressure, we get the amount of molecules that would be in that pore at those specific conditions in equilibrium. After running several simulations, we have what we call adsorption isotherm. Adsorption isotherms can have different shapes, shown in this table. Each shape is a reflection of certain characteristics of the system. Our fictional isotherm on the left would fit best the standard type 5, which is common in systems where the adsorbent interacts more strongly with itself than with the adsorbent. A good example of that is the adsorption of water in carbonaceous materials. So in addition to telling a lot about some characteristics of the system, adsorption isotherms can be used to create a pore size distribution of a certain material. That type of analysis is very important on the characterization of porous materials, which is the ultimate goal of my research. Well, this is it. Thank you for watching the video. If you have any questions or comments, please contact me on this email and I'll be happy to answer them. Have a good one, and I'll see you in the next video.